So one option that I'm looking at is using ammonia to store the hydrogen. So ammonia can be stored as a liquid, and so we have a higher density of molecules. And you can see that ammonia as a liquid up in the top is has 4 times as much energy density as hydrogen at a high pressure. It's used as a fertilizer, so it's a chemical that's widely available, and it can be decomposed. So the ammonia can be decomposed to form nitrogen and hydrogen in order to run the vehicle. So the idea is that you would produce ammonia in these large chemical plants. And ammonia would be distributed to local filling stations, just like gasoline is. You would fill up your vehicle with ammonia, and then inside the vehicle, you would turn the ammonia back into nitrogen and hydrogen, and this hydrogen would be used to run the fuel cell, which would power your vehicle, power your car. So what my research actually focuses on is trying to optimize this reaction and trying to make it happen at a lower temperature, so less energy is required. And one way to do this is to use a catalyst, which is what Mike talked about last week. So this is Mike's slide from last week, and basically, if you look at the blue line, this is the activation barrier needed in order to combine A and B to make a molecule of A and B. And you can see with the catalyst, where the atoms are absorbed onto the surface, it lowers the activation barrier quite a bit to get to A and B. So that means your reaction is going to happen at a much faster speed. So ammonia decomposition, if you break it down into, these are called elementary reaction steps up in the left-hand corner. So it's the addition, the absorption or desorption of a molecule, or adding or breaking one bond. You see that there are 6 reaction steps, and for each of these reaction steps there's an activation barrier. So what we have, which Mike also talked about last week, is we have your reaction coordinate where you can have multiple activation barriers in order to get to your product. So each metal will result in different activation barriers. So say platinum gives activation barriers such as the black one, and then maybe nickel gives separate activation barriers, which are like the yellow ones. What we can do is we can do modeling, which is what Mike talked about last week, in order to figure out which is where you combine all of these different activation barriers together and model the reaction in order to see which metal is the best for the reaction. And so a catalyst can be composed of one metal, or it can be composed of many metals. For my work, I work on catalysts that have one metal, or combining it in order to have 2 metals. And the main metals that are used for catalysts are the ones highlighted in orange. So this is a display of the reactor that I use, a computational reactor. I'm guessing some of you guys have had algebra and differential equations a little bit. Yeah. So basically we use differential equations and algebra in order to solve the reaction. And so we set up our differential equations and algebraic equations, and we also add the different activation barriers, which are parameters in the equations, and we add operating conditions, and we solve the differential equations and algebraic equations in order to get we get conversions. So how fast the reaction happens, we can get reaction rates out of our reactor. And this is a really powerful tool because if we were to actually do this reaction, physically run the reaction, we'd have to create the reactor, we'd have to create the catalyst. It takes a lot of time. You vary the conditions, which will all change your actual conversions. So we can do this all by solving a couple of equations, by solving 9 equations. And so it's cheaper, it's faster, it's very advantageous. So I looked at how this reaction, or the reaction rates for a number of transition metals that I showed you on the other slide. And we can model it for each of the different transition metals. And the red dots are the dots from the model, and the black dots, or the black triangles, are the experimental data. So you can see we get a relatively good fit between the models and the experimental data. And we can start using this to predict new catalysts. And if we want to, this is actually called a volcano curve, and what it is you plot the activity, so the conversion, as a function of some parameter or some property of the metal. So this is the binding energy of a nitrogen atom to each of the different catalysts, to each of the different metals. And it's something that doesn't change, and it's a property of each individual metal, but it doesn't change depending on what's on the surface. So if we were to start trying to predict alternative or better bimetallic catalysts, or better catalysts in general, we want to try to find metals that have binding properties near the optimal, near the top of the volcano, which would be in this general region. And I just had a little fact. So we can try to optimize catalysts this way and find new catalysts this way, or in the past, when people didn't really have computational methods, catalysts were discovered by trial and error. So you just try mixing different metals together and seeing what the conversions were, seeing how active they were. And for this particular reaction, which is actually the ammonia synthesis reaction, the catalyst that they use in industry now was discovered by testing over 2,500 different catalysts in over 6,500 experiments. So that took a lot of people many years in order to find the optimal catalyst. But we can start looking for optimal catalysts by using this modeling technique. So we actually have a computational tool